Good morning, first of all. Welcome back, and thank you for coming back. I thought after yesterday, maybe, I scared you a little bit. I try not to give you too many details. Again, my purpose here is to see how those tools can be applied and what scientific question we can answer. So I want to acknowledge one question I received yesterday, so thank you so much for asking this question, and maybe share it with you. So the question was, how fuel type influence PAC emissions in wildfires? So moving a little bit from the simplified lab scale that we have seen to those. And so just to summarize also a little bit what I said yesterday, the fuel type and the load. So what kind of vegetation is burning is very important, right? The dry grasses, brush, ponderosa, pine forest, slash, how dense it is. Those are the questions that you want to ask when you assess those things. So before the firefighters are sent out, you need to have an idea of what type of fire you're dealing with. And so questions related to you in terms of chemistry and pHs that we studied is, so how dense it is, and different fuels burn differently. So biomass, yesterday we mentioned this a little bit, as a higher volatile matter like cellulose, lignin, and even potassium salt that can produce, for example, in some cases, more pHs. When wildfires burn into urban interface, this has become way more complicated, so what we call the WUI, that you start consuming vehicles, homes, waste, and the emissions are way more toxic. Okay, so the type of pHs or hydrocarbons that you form are different. Yesterday I showed some examples. Do you remember the one with the 5-member rings and an oxygen that we look at the pathways? This is a furane. It's one of the, similar to dioxin. So it's basically a very carcinogenic species. And so depending on the condition, but also what you're burning in these things, the emission can be more toxic. Plastic, high quantity of pHs, sometimes hundreds of thousands times more than burning natural wood in similar conditions. And these fires also release other substances, like the one I mentioned yesterday, furanes, metals, and other things. Okay, so just to bring a little bit of the chemistry to these more macroscopic scenarios, the type of fuel and the load, how dense, is going to influence the type of pHs. Okay. What do you think is the effect of potassium salt on soot? Any idea, more or less? Well, yesterday we talked a little bit about nucleation site, okay. What else? Any idea? Is that good or bad, first of all, for soot? What do you think? Because yeah, in the previous slides I said, this also is a, what did I mention? So those are all the things you consider. So potassium, they all contribute somehow to more or less pHs. So those are one of the parameters that you look. So you remember yesterday that we looked at those radicals, and I said, hey, there are these very stable radicals that propagate also reactions. So it's easier to build some benzene and keep going there. So what the salt does, so potassium species, what they do, they scavenge key radicals, like a hydrogen OH. Do you remember we talked, for example, about the HACA? I said you have a benzene, you remove a nitrogen is removed by another hydrogen, then you add acetylene, and then you keep growing, right? So you do need acetylene, but you need also hydrogen to grow. And so if you have some species that can scavenge key radicals like a hydrogen, that they are essential for pHs, then you are kind of terminating this growth mechanism, okay? And so the effect is that can reduce this kind of polymerization reaction that leads to pHs, okay? So a little bit what I want to bring in is some of the concepts that I covered yesterday and how you apply to real questions. The other thing that goes back to what you suggested a little bit, that what happened, once those salts are on the surface of soot, they can act as a catalyst. So what they do, they promote the rate of oxidation of the solid carbons. Okay, and so they promote reaction between the carbon surface, the particle, the nanoparticle that you were looking yesterday, and some of those oxidizing agents. So burning off the soot at lower temperature and faster rates. So those are some of the consequences that you can have. And so they are also used just as in a particulate filter. So when you think potassium catalyst for those, okay? So don't forget what I told you yesterday. There is a lot of chemistry, but there is also, I think, an exciting way to make a connection between the information and real life. Okay, so don't leave it there as, oh, this is a soot chemistry. You can see practical applications. Okay, so let me go back to a little recap from yesterday, and I want to emphasize the problem, not the problem, the limitations. So I'm going to show you this again, and remember, I'm interested in this transition here. That's the key part here. Now, in order to make this transition, the first thing that you need to make sure of is that your model, I'm modeling, you have the right pool of hydrocarbons before they keep growing, okay? If your model has 4 compounds, for example, you're not going to match all the experimental evidence that come after. So if I want to look at this region, I need to cross with the right boundary conditions here, the right pH concentration. So DFT is great for this fundamental pH chemistry that I showed you yesterday. So you can grow 1 ring, 2 rings. You can also go to pyrene. And there are a lot of mechanisms, gas phase mechanisms, that go all the way to coronin. That is a bigger one. Not many, because the reaction becomes, you know, as I told you yesterday, they grow exponentially sometimes with the species and the isomer. So, but there are a lot of mechanisms that can get you here, somehow. But pH is challenging. There is a vast reaction pathways, isomers. We discussed this yesterday. Now, DFT calculations are expensive. So I can do benzene, I can do pyrene, but when you get to, I don't know, maybe 20 rings, what do? You don't do an DFT. It's computationally too intensive. So I cannot keep growing just doing 1 reaction at a time, okay? Especially when I grow in size. So it's not going to help me, DFT. It helps me in this stage when I need to know, you know, what pathways lead from those precursors all the way up here. The second part is like a quantum chemistry. You remember yesterday we talked about PS. You have the reactant, you need to know the product, and then you find the transition state. But you need to know the product. So a priori, you need to have that kind of knowledge. So sometimes there is a lot of literature in which are the major classes in combustion, sure. But there are also things that maybe you don't see or you don't think about, or maybe some condition reveals to you. And so quantum chemistry needs information a priori on what products, you know, could be formed. What products could be, I don't know why I said, okay. So let me give you more examples of this variety, because again, some of the mechanisms aim to reproduce some of the component. So the formation of 6-member aromatic rings, it's very complicated, but there are different evidence right now. And again, with the tools, different tools, we talk about EM, AFM, there is a lot going on in optical techniques. And so instead of having, in addition of having only pericondensate, so species that are 6 fused rings, like the pyrene or the coronin, there are a lot of evidence that say that there are also aliphatic chains, there are 5-member rings, there is oxygen, and there is curvature, okay? So think about this. If you have 2 flat pHs and you want them to react, then it might be easier if they are completely flat, right? But if those species now they have curvature, the static hindrance becomes a problem. So you cannot just say A plus B becomes C. Curvature, if you want to be accurate, is part of the story. Now, why am I doing so much mess about all this? Because as I mentioned yesterday, I want to grow retaining the chemistry. I don't want to jump into spherical particles, okay? So I need to know what's the chemistry that's happening. So let me give you examples. Aliphatic carbon. This is just an experimental paper. It was AFM, and they imaging some of those pHs that were present on soot. And so from the images, they reconstructed some of the structures. So what you see is definitely 6-member rings, you see 5-member rings, and you see some chains here, okay? And here are other examples. So there is a big variety here. Same, another AFM study shows that you have those kind of scenarios. You have the 5-member rings, and there is different peripheral pentagonal rings. Okay, so I have something that looks like this. You see, you have a 5-member, but there's a carbon with 2 hydrogen here. This is a 5-member, but I have a double bond. And so, different variety. Okay. More. This is a paper that studied the co-flow diffusion flames, and it was for jet fuels, so jet A1 surrogate fuels. And what they measure, and computed also, is that as you grow in size, so this is 30 millimeters and 40 millimeters in the flame, basically, 50 and 60. This is the oxygen-carbon ratio that you see, okay? And so basically, as a function of the molecular weight, if you want, you see the concentration of oxygen. So the oxygenated compounds, 200 and 600 AMU, this is the mass range, and the results so oxygenated were abundant in all samples that they were sampled, okay? So oxygen. Another flame, independent, this was a paper I worked with the experimental group at that time was Sandia, and they had a premix ethylene oxygen flame. Okay, ethylene oxygen, hydrocarbon oxygen flame. So there is no oxygen in the fuel, well, I mean, in the fuel structures. And still, you're burning this hydrocarbon flame, and this was with X-ray, photoelectron spectroscopy spectra. What you see here is the fraction of COH, COO, and COO species at different distance from the burner. So this is the distance from the burner, so this is 0 and this is 10. And what you see that as you move along the flame, what's happening is that some of this one, for example, that is a COC, goes up and then goes down, the COO, and then this is the COH. The idea is that you form those structures that they have those kind of insight, basically. And this should be part of our story. Okay, you should not just remove them. So, okay, and I have also the reference in case you want to see more. Okay, what if? What if I can tell you, or I propose you, that we can develop now a method that allows to grow in size but retain chemical information. So I can go to 200, 500 carbon atoms and I still have my chemistry. What if this method does not require a priori information? I mean, you don't need to know that if you have A and B, produces C. You need to have information about who A and B are, otherwise you don't know it. But spontaneously, it will, given some rules, it will evolve, okay? So you can build in the structure. And what if this approach were able to reproduce the pHs in various conditions? So not only the fused member, not only the aliphatic chain, but maybe oxygen and maybe 5-member rings in the variety of experiments that I showed you. So let's see what I have here. Sorry, here too. Okay. So again, we are going to jump now today from the gas phase chemistry with DFT that brought us somehow in those initial pHs all the way to these structures. Okay, I'll show you how to do that. And there is 2 techniques that I want to talk about. I'll promise not too many details. And again, feel free to ask me any questions at any time, even later. But kinetic Monte Carlo, the first one, and then molecular dynamics. Why I need both? First of all, why I'm giving you so much information at this time. Look at these structures. First of all, there is, if you want, a size, but also a time scale problem. Okay, I need to advance. I am here, I need to jump to get to in time and in size to move forward. Kinetic Monte Carlo is a technique that allows you to jump in time, for example. Okay, so we can take longer steps if you want. Once you have structures like this, or bigger like this, you can have rearrangement. So you have these structures, but you know, remember some of the DFT I showed you yesterday, there was one with the 5-member rings that was open and then eventually closes? That's a kind of rearrangement. I don't need the things from outside, but just because I'm on the surface there, they like to move around. So, and this is a completely different time scale. So I need this intramolecular rearrangement are on the nice scale, 1 nanosecond, 1 second. So it's a completely different scale and type reaction that you can have here. So So I do need something different. Again, I want to grow and try to be as accurate as I possibly can. Okay, so we're going to do this for kinetic Monte Carlo, and then we take a break. So hang with me here, and I'll try to not to bog you down with too many. Okay, so first of all, why do we need this? The majority of the chemical mechanisms that you have right now, they grow up to a size, but they've been focusing historically on species that look like this. So those are stabilomers, some products that are produced like also from equilibrium reaction. So they are a very stable product in which you have fused 6-member rings. This has been the main interest. There are a lot of new stuff going on, but historically this has been the thermodynamics that have been driven the formation of those guys, okay? But it's not that simple. So again, some of the other examples that you see in flames, you can see the red is oxygenate and blue is hydrocarbon. So people have found a lot of those oxygenated species. They have found, again, different aliphatic, but also aromatic. So when you have those stable species in which are fused, so think about the haka. The haka has one ring, then you have attachment of an acetylene, and then you close, right? So the closing is very stable. But why we are not forming also those kinetic products, so the ones that are intermediate, why they not survive there? Why do, if you observe different structures of soot and aliphatic chain, oxygen, why it doesn't react when you have a nanoparticle? I'll show you that. If your structure is as an oxygen and find another structure with oxygen, they will repel each other. And are all the conditions dominated by the same reaction pathway? Again, it's too vast to do with the technique that I saw. So it's important to develop, I would say crucial, in the community to develop models that can explain all the data, not a selection of it. So first to take away slowly, the species of the reaction that involve soot are in the millions, first of all. This complexity is not captured by simplification, although they have a place in some context, absolutely, but there is no guarantee that different flames form soot through identical sets of reactions. Okay, so these are changes. So I'm going to talk for a moment about the chemical master equation, and I'll try to simplify that. So I don't want to have an average concentration of species. I don't want to look at average behavior. I want to dive into this kind of scenario, box if you want, in which you have a species, think about the flame, there is a lot of small fragment around, and eventually they grow, okay? So often this system is described by macroscopic quantity, the concentration and the rate constant, as I told you in DFT. Those are average concentration of the species. So you know that in this box there is an average acetylene of 10 to the minus 2 mole fraction, for example, okay? And the differential equations usually are continuous and deterministic in this case. But the reaction happens one molecule at a time, okay? You have one. So this is more discrete. So remember, my goal is to describe this at this level. So I need not to go with something that is the continuous and deterministic usually, but maybe the reaction happens at discrete, and the reaction happens at random time. Okay, it's not a continuous. Maybe they stay for a while in some kind of dancing, then they react, then they jump to the next one. So it's a stochastic event. So the chemical master equation describes the time evolution of the probability distribution of the number of molecules in the chemical species, and they account for discrete and random nature of the reactions. So if I want to describe this, what I'm saying is if I want to describe this system at this level of detail in which I look what reaction is happening, then I am looking at discrete and stochastic. And the answer to this is the chemical master equation, okay? It's complicated, not easy to solve. So what do we do? So the chemical master equation, they have like what they call a state vector, I want to say. And this is the number of molecules of each species. So you can have acetylene, you can have oxygen, you can have hydrogen. And then this is the variation vector for a reaction. So change in number of molecules of each species. So think about, I don't know, if acetylene is broken down in, let's do ethane, maybe it's easier. Okay, so if you have, let's say, C2H6 and it breaks down in CH3 as CH3, now the number of molecules is changing, right? And so this is basically what is taken account. So using those two, the chemical master equation tells you that the probability to be in a state S, that the vector I just showed you, at time t, starting from S0 at time t0, okay? So do you have this P over time, and you can define this as reaction. So think about a state here, you're a state 1. So this is function of everything that happened before and after. So the reaction from other states to get to this point, and the reaction from this state to the other state, okay? So some complicated math. The point I want to just tell you, think about the physics, because we are looking at this level of detail. And so if you're interested, this is an amazing, complicated paper to read. I read, I don't know, 10 times to try to understand something, but it's amazing. So, and so the rate constant, in this case, the rate constant is derived by the propensity of the reaction to happen, basically. So what do we do? Well, this chemical master equation is a rigorous mathematical framework, but it's complicated, okay? But allow us to move beyond average concentration. So again, no average concentration, but exactly what are the species in that box that I'm looking at. So what is the physical meaning? The physical meaning, this is again the expression that you have seen. So instead of, again, looking at the average concentration, this tracks the probability of finding the system in a state, okay, at a given time. So this is a potential energy field surface, if you want to. And so the blue are some kind of dips. You have seen yesterday, PS, right? And then you go up and down. So this is, for example, reaction happening here. Eventually, you go over the transition state, and you end up in a new thing. So the system spends time in a state, as you can see here, and then jumps to a different one. Okay, so now maybe you have the addition of 2C3C3 and you jump and now you have a benzene. It's a completely different state. So randomly, this is what's happening. So one of the problems with this algorithm, it is great, is that you have a fast reaction. And then you have reaction that it takes a lot of time to happen. So especially in combustion, you have some very, very fast reaction, like I told you yesterday, C3 plus C3, okay? But then you have that reaction that takes much longer, that they need to dance around for a while before they find the bond. So this is a stiffness, and the problem is that it doesn't work well with this equation unless you do some approximations. So there are different algorithms that have been trying to fix this problem, so kinetic Monte Carlo. And without too many details, what I want to mention is that an approximation that is being used very widely is to assume that this CI that I showed you before, so let me go back for a second, S, so the concentration of those individual number of molecules or each species does not depend on time. Okay. And so if they do this kind of approximation that you see here, it's easier to code, very easy. But it's problematic if the condition changes rapidly, like combustion, temperature, pressure, they change those reactions. So this is appropriate, if you do that, for fast reacting low temperature systems. Like, you know, you're polymerizing at very, very low temperature. Combustion is not that. I told you that was one of the challenging and fascinating things for this reason. So what happens? Well, we can do some simplification. So the first thing that we need to do is look at what reaction event happens, okay? So A plus B becomes C. And then when the next reaction event will occur. So the residence time or waiting time. And then after that, the system jumps to the new state that is basically this reaction, dictated by the reaction that you do, okay? And so what I'm showing you in the next two slides, so I'll give you the preview because I'm a little bit packed, is that a series of modeling for chemical kinetics, starting from the highly detailed, that is the chemical master equation, for small system and fast reactions, okay? I need to bring you down here. Then we'll move quickly through an approximation, and this is the chemical equation, Langevin equation, But this is a larger system, and then we will end up with continuous deterministic models. That's what I want. I wanted to find a way to describe the box that I showed you in this way, in which we look at ordinary differential equations that are valid in the thermodynamic limit. So this is not enough for me because it's a small system and fast reaction. What about a lot of molecules? The flame is a huge amount of the species, I told you before. So this is not good. I need to move. And the way I move here, now I jump to this one that gives me larger system. Not enough yet, because now I'm losing also the fast reaction, and then we will get here, okay? So first thing, how do we scale up? Fast reaction, so I'm focusing on fast reaction, important in chemistry. So the idea that I show you is that the discrete and stochastic is what we want to look in the box. Then you can use chemical master equation or stochastic algorithm, the previous one. Complicated. We cannot afford that. So we can do what they call a leap condition and start and do the next step. So in this scenario, the reactions are fast and time independent, okay? So the reaction doesn't care what happened before. That's, again, is an approximation. So each reaction instead occurs multiple times. Okay, this works. And so with those approximations in the leap condition, you can go to continuous and stochastic. That's what I was talking before, in which now you can deal also with the bigger system. And so there is more chemistry here, but those are the equations, okay, that describe those cases. Still too complicated. They offer continuous time approximation for the discrete, so they're an approximation of the one above, but they are useful for systems with the moderate to large number of molecules. So not good yet for me. And so we take one more step, and now we scale up from this guy. Now, the thermodynamic limit, it means that you have a huge system, so it's a large enough number of molecules. Then with this approximation, you can jump into what they call continuous and deterministic. So you can talk about reaction rate equation, linear noise approximation, but the chemical Langevin equation reduced to this kind of expression. And this is what we want. Remember, I am looking in the box. I know S. I have some information. What are the molecules, acetylene, hydrogen, oxygen, because I have from DFT, right? So I can do that and still related to the rate constant in this case. So all these approximation, all those two slides if you want, there is a lot of theory that I'm not covering, but allows you to look in the box and keep a discrete stochastic event and change it into with some approximations that we need to take care into the algorithm, but I can still define my rates looking at the individual molecules, okay? So what happened to this one? What is the main conclusion? And again, if you guys, I didn't want to talk about all those reactions, the chemical equation, there is no point here. If you're interested in any of those systems, maybe if you're studying only very fast reactions, or some other approximation, you can look them up. This tells you what technique is the best. My point is to bring you here, in which I can have my rate as a function of this vector that I showed you before, in which I have the number of the molecules. So for chemical kinetics, there is an hierarchy of approaches from discrete stochastic, that will be for small and fast system, to continuous stochastic for larger ones. And then we can, with some approximation in the algorithm, we can look ordinary differential equations that are valid in the thermodynamic limit. Thermodynamic limit means a big system, big enough system, okay? And so kinetic Monte Carlo method can be used to sample the evolution of the system under very general conditions. So I went from the chemical master equation all the way through some algorithms that allow you to approximate the system, and I can use somehow kinetic Monte Carlo. So this is a code that I've been developing for years now. And you know, sometimes I always look for students who are interested in keep developing this. But it is one of the things I'm proud about, so I'm going to talk a little bit about this. So students named it the Stochastic Nanoparticle Simulator, okay, SNAPS, that's the way they call it. And so what this does is a kinetic Monte Carlo code based on some of the assumptions that I gave you before, and allow you to look at the box of the species and see how those species evolve. So first of all, there are no assumptions on reaction rates and quantities or equilibrium, okay? We only talk with this system a generic reaction. So this code does not say like C3 plus C3 becomes benzene, but it tells you maybe if you have a radical on this site and find another radical on similar site, you could have this type of output, okay? I don't know a priori what is the output. The code decides. Is time dependent. Remember one of the critiques I was mentioning before in my flowchart that people solve the algorithm with the time independent. So they say the evolution of my species doesn't depend on what happened before, okay? And so we were able to implement also this, so went down and does a kind of approximation. And so the reaction propensity depends on possible states before and next reactions. This is a critical, I would say, most critical part of the story. So what do I mean by this? First of all, in this code, what we do, we have some kind of structures. And what we define sites. So I'm not defining these as, I don't even know the name of the structures, but this is something blob that has, in this case there is a carbon, but this carbon is on an aliphatic chain with a double bond, okay? This one is a carbon on a 5-member rings with a double bond here, single bond, and has one hydrogen attached. Okay. This one is on 6-member rings. So, and you keep going like this. So you define the sites as generic as possible, and you have some information also about the neighbors, the surroundings of the system. And this is the time that I was showing. Okay. So how does it work? So I'm going to look at this box again. So as input, when you want to run the simulations, you need some environmental conditions. So I need to know what is the temperature and pressure of the system, first of all. I need to define this box initially. I need to say, okay, and I have some species. I have acetylene, I have C3, I have hydrogen, I have OH that you see here. I need some information from the gas phase, the DFT that we talked about before, right? And those species are easier to measure than when you grow in size. We mentioned that. So there is a lot of mass spectrometry, for example, that has been done on molecules, small hydrocarbons, but there is very limited on the transition. So what I mean is that what I put in the box as the initial condition is pretty reliable, because before doing that, I compare with experimental data. The second thing is that you choose some molecular seed. So initially I can say, oh, there is a lot of benzene that has been formed, right? How does benzene evolve in a flame? So and you can choose also different species. Doesn't matter, naphthalene, cyclopentane, doesn't matter. What you do also, you add the generic mechanism. So a set of generic reactions. Yesterday with DFT, I gave you some study that we reported in the literature. I told you that I collect everything. People produce reaction rates. I love them. That only, what they do, they help me to create this mechanism. And I'll show you what that means. So reactions are added in pairs. So remember, I'm still defining my box. I have not run anything else. I need this combustion condition. I need a list of reactions, possible site reaction. They are added in pair. One thing that we really care about is that you have thermodynamics, they're consistent. Sometimes when you have a mechanism, people add the forward reactions or a reverse reaction, but you need to make sure that the thermodynamic property are consistent, right? So you have the forward. If you have the thermodynamic, you can get the reverse, right? Well, sometimes this is not respected. This is very important. All the reactions are also reversible. You can say there is only one way. It's all reversible. And they should lead to the correct equilibrium constant. So that's very important. Right? And so right now we have more than 430 reactions possible. And we are continuously expanding. So the more people produce DFT for pathways, even for small molecules, the more help us, because we can translate. And right now we have organized those DFT in 5 groups and type of bond. So let me give you an example. And I have a few slides like this. to bore you a little bit. But so forget about the specificity. What kind of reaction have I seen? Well, I have seen the one involved carbon-carbon bonds, like, and so, for example, carbon fragment addition to an aromatic and aliphatic carbon, right? So the formation of 6-member rings, like the HACA. Or the formation of 5-member rings in which you have a HACA, but you have a bay closure and C3 growth. So what I mean here is that, again, propargyl going up, but you can have a bay closure. You remember yesterday, again, the 5-member rings, it can rearrange and then eventually can close also. So you can have a situation in which you close the 6-member rings to that. And so the generic reaction, so as you can see here, this becomes like a ring, right? You have a carbon, and now those attachments, the neighbors, they become R. And so what you define in this case is all the gas species that you can have in the system and in your box. There is some definition of molecules that is important, the way we define the molecules, okay, the index. But the point is that I don't care about anymore about RRR, but this has become a generic reaction. In this case, I have an addition of an R to the 6-member rings. You see here? With this another case, you have a 5-member rings now with the carbon here. Remember, my goal is carbon-carbon bond. And I have any R that can I define in my list that attaches here. I have all those other type of reactions, okay? Again, from quantum chemistry of yesterday. More, because I want to show that we try to be comprehensive and implement everything. So those are all the other scenarios that we have in the code in which we transform the specificity of the carbon into neighbors they call R, okay? But we try to include as many pathways as possible. Of course, there are approximations because I get rates from quantum chemistry. Some are not accurate. Okay, so there is a lot of, there is an error that definitely is, I'm not claiming everything perfect. So, more of those. Oh, look at this. This is the one from yesterday, for example. You remember there was something like this, it was open, and then you can close it with the system. Okay. So we include really everything, even the formation of, 6, and the formation you close to a 5-member rings on the surface here. Remember some of the experiment that I showed you? They saw the 5-member there. There is also open chain carbon site that are important. So this is, again, all the reactions that we try to include. There is a big work, there was one PhD student that just started thinking about the family of reactions. Because, again, a lot of literature, a lot of possibility. How do you group them? And I have a lot of them. This is cool also. This is a 5-member rings with the carbon. You see the radical here? Again, you have RRR. And this can transform in 2 6-member rings. So this is also something else. So we try to include this structure. I refuse to go over this, but I want to tell you that there is oxygen also. Remember yesterday that we are doing some work on benzofuran and the oxygen inside? So we also included that for that. Okay, too many. Okay, so trust me, and I have all the reaction for you in the slides also if you're interested in looking at them. Okay, that's it. We also included what I told you yesterday. Again, you went, just as a reminder, from a benzene in this case all the way to something, a furane with oxygen. And in this case also is another example that I didn't show yesterday, but you can have a structure that looks like this, which you have some kind of bridge in between. And there are many pathways for this, and eventually you can have, if there is oxygen enough, you can have oxygen embedded in your structures. So not present at the beginning, but you find a way to embed them. That's very important. Why this is important? Because when you have these bigger structures and he finds another one like this, they will repel each other, okay? With oxygen in some cases. Okay, so SNAPs, it basically implemented the kinetic Monte Carlo method that allows me to simplify the chemical master equations with some of the approximation that I show, including time dependence. Now, it can capture some of the reactivity, and I use elementary reaction. I use result from GFT of yesterday, okay? I don't use elementary reaction. It means you take all the steps one at a time, okay? I don't jump, I don't say benzene, equals this guy, benzene plus oxygen or whatever equals this guy. I take care of all those steps in between, all the elementary reactions. And then is reversible and thermodynamically consistent. This is a very important point. I have seen a lot of gas phase mechanisms which you add the reaction and is not consistent. So my intent here is to tell you also about many of the things I have seen in the literature, and I think you should pay attention if you're developing anything as a student here. So this approach, this SNAPS approach, is not limited to combustion. It's a generic algorithm. And we have been using these in non-thermal plasma results also, and CVD situations, for example. Lately, I've been used also the PFAS, that is one of the pollutants that we have. Anyway, just to the complexity. Okay, well, let's take a look at what's happening here. Okay, so for the approach, I have environmental condition. I have to choose my molecular seed and, where does it start? And then I need some reaction mechanism, generic form of all this. I want to acknowledge the errors because, of course, as I told you, I'm collecting data. If there is an error will propagate to KMC model, right? The seeds is formed at different times, evolve differently. So this makes sense. So think about this. If you are looking at benzene at 1 millimeters from the flame, or you're looking at benzene because it's still there, but you are now at 5 millimeters, the environment around is completely different. So it will evolve different trajectories, right? So this is something that we can reconcile and we include. And then the reaction mechanism allow us to test different pathways. So I'm not saying anything about which one is important. I will let the system evolve and decide the relative importance of the species. So what happened is that benzene, you start putting benzene in that box and will evolve. Okay? You have different trajectories. So this is an example, just to say, from this guy, you can add other species or you can lead to these structures eventually. This is another option. Now you have the same seed, right? The same conditions also. And this is another option. So we run tens of thousands simulations for this. And this is defined as an embarrassingly parallel code. Okay? So it's hugely parallel for that. Okay? And then the problem is now I need to extract information from each molecular history and considering the species lifetime and the amount of seed. So there is a lot of post-processing that happens, but the point is that this is a lot of data and information. So, people who are developing overall empirical Soot model, again, they don't want this. They want a number. So you need to somehow connect all this information to macroscopic parameters. Okay, so here I have just a movie, a snapshot that I want to show you, one trajectory. So you start from this kind of compound. I can start from any other seed, I told you before. Like what you see, excuse me, what you see here is that the green is carbon, white is a hydrogen in this case. And again, this is in the box, so there are species around that possibly could be added, depending on the way the system evolved. And so what you see here is the evolution, so there are different snapshots taken at different times in the flame of one trajectory, so how that initial seeds evolve in this specific environment, in this box. And so we'll start from 2 naphthalene, or 2 6-member rings. By the time this ends, you will have about 200 carbons. But what is interesting is that, first of all, you start from a structure that is flat, like the one I show you, and you end up with 3-dimensional structures. Okay, you have the formation of 5-member rings and some aliphatic chains in this case. It depends on the condition, but you have curvature also. Okay, so I don't know exactly. So, for example, you see here one of the aliphatic chains. Again, I'm not giving them specific information on what the species. I don't even know the name of the species, but the system is evolving with those generic reactions. Now, if you think about fullerenes are formed in flames. You remember I told you yesterday. This kind of approach, given the condition, could also be used to form some of those buckyballs or structures with the curvature. So this is just a movie, and this is one of the trajectories for the system that we can produce with SNAPS. Okay. Question number 1, wonderful. how does this compare with, you know, if you have a kinetic mechanism, a simple gas phase mechanism, there are many in the literature. They go all the formation, again, to benzene or pyrene. Let's talk about this. So if you take, for example, a chemical reactor, and you say, I'm running this gas phase mechanism, and for the same condition, and I want to compute benzene concentration. How does this compare with my snaps? So we did some study, and there were 2 experimental flames that we look here. And what you see here is over time and the mole fractions. This is a constant temperature. And so the comparison is, I didn't see very well because the agreement is good. But anyway, the chemkin is this dashed line that you see here. So this is the benzene concentration mole fractions over time versus the result from snaps that you get. And this also tells you something about 100 trajectories versus 1,000 trajectories. So you need more convergence. So it tells you also with that. Yeah, the uncertainty is related to number of simulation. Okay, so you need to be careful about, you need to make sure that it's convergence. You cannot just that. And this is also another comparison that we did. Now the time over here, and this is the mole fractions. And what you see is basically, this is the temperature that is now changing over time. And this is the comparison again from a chemkin type of result. So with the differential equation, right? Because chemkin is solving the ODE to our kinetic Monte Carlo approach. So remember that I went from there all the way here. Okay. So let's take a look now at an example. So we have compared with many experimental data, and I want to emphasize the point that especially if you do modeling, you want to always work with people who do experiments, okay? Modeling, you can model everything. Someone needs to keep you grounded. So experiments are very, very important. So I want to show you some results. So this is atmospheric pressure, ethylene, oxygen, argon, counterflow diffusion flames. Okay, so counterflow diffusion flames, this is the flame that you see here, and the oxidant and the fuel are coming from the opposite jets, if you want. Okay, so the first thing, premixed flames are easier. Premixed flames, you can decouple the chemistry from the fluidodynamics. And this is the reason why they are used for many lab experiments, because you can really focus on the chemistry, right? But reality is more complicated. And so this is maybe the first step in terms of complexity, and in which you have those 2 streams getting together. But the idea is that you need a CFD now. Okay, you cannot just, you need to solve the fluidodynamic a bit. So for this specific system, so let me see, first of all, this is the distance from the burner, and this is the distance from the center line. So this is your flame, so the radial going in this direction, and this is the height, right? So this DFO is the distance from the 2 jets. This one is a lateral. Why I kept this study, why I was interested in this study. So the first thing that I want to emphasize is that people usually experimentally, what they do, they sample the center line. If you look at the literature, people say, okay, I am in this flame, sorry, the one I showed before, and they sample here, okay, this port here. What I'm going to show you is that those pHs evolve differently whether you are here, 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 or here, okay? And so sampling this is an average, definitely a good thing, but there is more chemistry going on those radial distribution sides of this flame. So the first thing that we did, so again, this is the height and this is the radial that you're looking here. And those are the streamline coming from the fuel flow and the oxidizer. So oxygen on top and bottom. So first of all, we did some simple CFD simulation for gas phase modeling and to describe this flame. So we had the streamline of those simulations, and we validated as a first step against temperature and gas phase species. So we use remember, to get to snaps, I need the boundary condition. I need to know the small fragments. So we got those this time through CFD, because I coupled the chemistry and the fluidodynamics. Then for each of those streamline that you can see here, we had the concentration of all the species in the gas phase. And for each point, we created our box with the snaps, and we saw the evolution of those pHs. So how did they change? This also plot is showing you the temperature, just to have an idea. The blue is 1800, okay, so that's our temperature. So we did 32,000 snap simulations. It's a lot of simulations. And we had 3 different seeds that we were interested in this case, and 110 origin points. So what this means, origins, is that, again, my box is located at different points to the streamline. I need to have the right environment. Benzene formed here will be different from benzene formed here because the environment is different. So the flame, well, has a cylindrical symmetry in this case, but the probe was here. The experimental probe was here, so we sampled around the probe also. Okay. The first thing that you notice, so to meditate, is that there is an asymmetric distribution of species. So this is, again, the radial distribution, and this is the height, and those are some of the compounds. So you have OH, and you have to look at this blue and green in this case. So then you have oxidizer, and then you have C3H3 and benzene, okay? So they are not symmetric, but they are influenced by different conditions. The CFD is one, and the flame front here. So what experiments did people measure? The first one was, so they look at some mass spectra. And those, what you see on the top in the experiment is the mass, the molecular weight of the species that they sampled in the main region here. And so this is the variety of molecular weights, can correspond to hundreds or more of species, okay? And this is the type of spectra that SNAPS was able to reproduce. And I think this is an amazing result. It's not perfect, sure, but we can feel this spectra. So somehow SNAPS is able to create all those species that if you look at just deterministic gas phase models, you don't see them. So this is, first of all, a great agreement with the experiment. And I will say that this agreement here that you see depends on how unstable the species are tallied in the simulation, okay? And also the probe effect. So there is also errors coming from the experiment and, of course, from the modeling. So again, all the species were seen as SNAPS. Another result is that in terms of the spectra, they were different species were identified. And so here you see that you have hydrocarbons, you have mixed peaks, and then you have oxygenated peaks. So if you do A, B, and C, okay, and I'm moving radially, so not in the center line, what you see in the spectra is that A, B, and C, you have different distributions. This is a rich variety of pHs that somehow you need to take into account if you want to develop a predictive model. And so just if you move along these streamlines, for example, you see that the species, the molecular structures changes. And so those species, the one with oxygen, the one with the 5-member rings, and the one with hydrocarbons were all included in the SNAPS. So another reason why I was interested in SNAPS, or I was excited about SNAPS, is that because it was producing all those species, in addition to mass spectra, SNAPS is also able to produce molecular structures, okay? And so there was no validation of our SNAPS for those weird species until 2019, when, again, this AFM study that I showed before, and here is some of the species, reported that those structures are actually present in those samples. And so those guys, in this case, the simulation of this flame showed that SNAPS capture most, not all, of the existing chemical groups. So this is a case in which SNAPS predicted species that then eventually were found in experimentally. And so in terms of agreement with this experimental work, we matched all the methyl groups, the 5-member rings, experimentally with some pHs with oxygen, like phenol and ketone, are matched. Like, for example, this 1 to 6 here, that you see 1 to 6. And then experimentally, there are few pHs, but the mechanism with oxygen reaction reproduce experimental distribution better. So, of course, there is some kind of, so those are some of the species that are also very, very important that we reproduce it. Okay? There's a 1,6. Disagreement for this specific experiment was that there is an overabundance of 5-member rings in this case, and unmatched the presence of this C, you see, triple bond CH, that is a key step in ACA. So, acknowledging the agreement, but also some of disagreement, and all this comes from different errors, as I was mentioning, and again, the generic mechanism that I have could be implemented more and more, of course. So I'm not done with the reaction mechanisms. Okay, takeaway. pHs or polycyclic aromatic carbons are more than just those fused rings, but there is a variety, and I show you that. They have complex combination of 6 5-member rings, aliphatic, and also different chains and oxygenated compounds. The kinetic mechanism describe those observations, all the experimental observation with some degree of accuracy, but different conditions may be dominated by different mechanisms. And again, some people that say, oh, this mechanism is very important, and then you run in a different conditions, might not get good agreement. So the idea is that you want to be generic. You don't want bias in any way the things, but you want to find a way to describe the system in a way that evolves spontaneously or without you biasing the product. And that's what SNAPS has been doing for a while. Sampling, so has also some biases that should be accounted while improving the theoretical understanding of reactions. Okay? So those are all things that I want to highlight, and I think we need to take into account. So expectations right now, what happens in reality is way more complicated, but you have all those other species. So to conclude here, also because it's very hot, what I want to show you, what I want to mention is that we have a way now to go from small benzene, naphthalene, or even pyrene, all the way to bigger structures, something that looks like this. Okay? So, and you can keep going. I'll show you the movie. You can get to structures that have even 2 nanometers in size as you go. Now, how do we move forward? So I'm going to stop now for a few minutes, and then we'll come back, and I'm going to move into another methodology, because now once you have those structures, how do they interact, and what happens on those reactions, on those structures? Okay, this is a different scale. Okay, let's take our 15 minutes according to the plan. Thank you.